Welcome to this video in which we will show how to use the Z-transform to analyze a system. The system function Hz of an LTI system is defined as the Z-transform of the impulse response Hn. Some important notes related to the system function are: the frequency response h(e⁻j theta may be derived from the system function by evaluating Hz around the unit circle. The Z-transform of a delay is z⁻⁻1. For this reason, we sometimes represent a delay in a signal flow graph with the symbol z⁻⁻1. The output yn of an LTI system can be described in time domain with the convolution sum between the input xn with the impulse response hn. In z domain, the convolution sum transforms as a product. Thus, yz is xz multiplied by hz. From this product, it follows that the system function hz can be written as yz divided by xz. By evaluating this function around the unit circle leads to an alternative way to find the frequency response h(e⁻j theta of an LTI system. An example is given on the next slide. As a first step, we describe the signal flow graph in the Z domain. That is, we interchange the time domain sequences xn and yn by their Z transforms xz and yz respectively, and we use the symbol z⁻⁻1 to represent a delay. The signal flow graph representation in the Z domain results in a simple algebraic expression between the input xz and the output yz. As mentioned before, we can find the system function hz by dividing yz by xz, which leads in this example to the given expression. By evaluating this expression around the unit circle leads to an expression for the frequency response h(e⁻j theta of the given signal flow graph. Applying the same steps to the signal flow graph and difference equation of a rational LTI system leads to the rational system function hz, from which the parameters are given by the weights bk and ak of the LTI system. Both numerator and denominator polynomials can be split as a product of first order terms. Therefore, the system function hz of an LTI system is defined within a scale factor b0 by the location of the poles alpha k and zeros beta k. In the module Z-transform, we have discussed the importance of the region of convergence, abbreviated as ROC. The table gives an impression of the region of convergence of 4 different sequences, namely stable, non-stable, causal and non-causal sequences. In the module systems, we have seen that bounded input, bounded output stability can very simply be tested by evaluating the sum of the absolute values of the impulse response weights. Multiplying each value of the impulse response by z⁻⁻n and evaluating the result around the unit circle does not change the tests for Bibo stability. Thus, Bibo stability implies that the evaluation of the system function hz around the unit circle must result in a finite number. Or in other words, the region of convergence of the system function hz must include the unit circle, which excludes the 2 indicated sequences out of the 4 possible sequences. In general, it's obvious that no poles may lie inside the region of convergence. Furthermore, we have seen in the module systems that causality implies that the values of the impulse response hn are 0 for negative indices n. In other words, the impulse response must be right-sided sequence. From the module Z-transform, we've seen that the Z-transform of such a right-sided sequence has a region of convergence which is outside a circle. which excludes the two indicated sequences out of the four possible sequences. Finally, a system can be realized in practice when the system is both stable and causal, which excludes the three indicated sequences out of the four possible sequences. And thus, all poles of a stable and causal LTI system HZ must lie inside the unit circle. In the following two slides, we will give two examples of a first order and a second order system, and these examples are of special interest because both first and second order systems are the basic building blocks for higher order systems. The figure shows a first order recursive filter with one feedback loop, which is weighted by the parameter A. Via the difference equation and its representation in the z domain, we can find the system function hz, which has, besides a 0 at z is 0, one pole which is located at z is A. According to the previous discussion, the system is both stable and causal when this pole is within the unit circle. This implies that the absolute value of the feedback parameter A of the given first order recursive system has to be smaller than 1. An alternative view of the causal and stable properties of this first order system can be found as follows. When the absolute value of the complex variable z is larger than the absolute value of the feedback parameter A, the system function hz can be expanded as the given geometric expression. Via the inverse z transform, this results in the given exponential expression for the impulse response hn. From this expression, it follows that the exponential function is right-sided and causal, and for the absolute value of the feedback parameter A smaller than 1, it is a decaying or stable function, which implies that the pole of the system is inside the unit circle and the unit circle is included in the region of convergence. A second example is the given second order feedback system hz with two feedback parameters A1 and A2, from which the poles alpha 1 and alpha 2 can be found via the given equation. When combining the expression with poles, it follows that the feedback parameter A1 is equal to the sum of the two poles alpha 1 and alpha 2, while A2 is equal to minus 1 times the product of the two poles. Together with the fact that the poles must lie inside the unit circle, we can find the given restrictions for the two feedback parameters A1 and A2, which can be represented by the so-called stability triangle. The region for complex roots is defined by the area below the given parabola, as depicted in the figure. From the previous discussion, we've seen that the poles of a stable system hz must lie within the unit circle. However, in some special cases, the poles can lie exactly on the unit circle and the system is, say, on the edge of being stable, as can be shown by the following example. The poles of the shown system can be found by evaluating the system function hz, which writes as the given equation. By using the Euler expression for cosine theta 0, it follows that the system has two poles which are located on the unit circle at angles plus or minus theta 0, as depicted in the pole 0 plot. As discussed in the module about Z transform, we can split this last expression for Hz into two first-order terms, which leads, via the inverse Z transform table, to an expression for the impulse response Hn of the given system. The system represents a discrete oscillator. In other words, when starting with an empty system and using a delta pulse as input, the system generates an output signal Yn, which behaves as a sinusoidal signal with frequency theta 0. The amplitude of this sinusoidal signal is equal to the constant c, which is equal to 1 divided by sine theta 0. As discussed before, the system function hz of a rational LTI system has a numerator and a denominator polynomial. Both numerator and denominator polynomials can be split as a product of first-order terms. Therefore, the system function hz of a rational LTI system is defined to within a scale factor b0 by the location of the poles alpha k and the zeros beta k. Note that each term in the numerator 1 minus beta k to the power z minus 1 contributes a 0 to the system function at z is beta k and the pole at z is 0. Similarly, each term in the denominator 1 minus alpha k z to the power minus 1 contributes a pole at z is alpha k and a 0 at z is 0. On the other hand, an AVR system consists, besides poles at z is 0, only of zeros. On the other hand, an IR system consists of both poles and zeros. If the impulse response Hn is real valued, the system function Hz is a conjugate symmetric function of Z. Thus, Hz is H star Z star, and the complex poles and zeros occur in conjugate symmetric pairs. Thus, if there is a complex pole or zero at Z is Z0, there is also a pole 0 at Z is Z0 star. Finally, we have seen before that the frequency response h e to the power j theta of an LTI system may be found from the system function by evaluating hz on the unit circle. In the following slide we will show how, for a rational function of z, the frequency response may be found geometrically from the poles and zeros of hz. As a first step, we rewrite the factored form of the system function hz by dividing both numerator and denominator by the terms z to the power minus 1. As mentioned before, the frequency response h e to the power j theta may be found from the system function by evaluating hz on the unit circle. Assume we want to calculate the frequency response at frequency theta 0 in a geometrical way from the poles and zeros of hz. The figure represents one zero at z is beta k and one pole at z is alpha k of such a system, and the location at z is e to the power j theta 0 on the unit circle. The magnitude of the frequency response is equal to the absolute value of the constant beta 0 times the product of the absolute value of the terms e to the power j theta minus beta k divided by the product of the absolute value of the terms e to the power j theta minus alpha k. Each absolute value of the term e to the power j theta minus beta k is equal to the length of the vector from the 0 at z is beta k to the unit circle at z is e to the power j theta 0, labeled v1 in the figure. Similarly, each absolute value of the term in the denominator e to the power j theta minus alpha k is the length of the vector from the pole at z is alpha k to the unit circle at z is e to the power j theta, labeled v2 in the figure. In other words, the contribution of the 0 at z is beta k and the pole at z is alpha k to the value of the magnitude of the frequency response at frequency theta 0 is equal to v1 divided by v2. This implies that when a pole is close to the unit circle, the magnitude of the frequency response becomes large, because the length of the vector v2 from the pole to the unit circle becomes small. Similarly, if there is a zero close to the unit circle, the magnitude of the frequency response becomes small, because the length of the vector, v1, from the zero to the unit circle becomes small. The analysis of the phase is similar. Assuming that the constant beta 0 is a positive real number, the phase corresponding to the frequency response as a function of theta is given by the equation. Besides the factor n minus m times theta, the phase is equal to the sum of the phases associated with the terms e to the power j theta minus beta k, minus the sum of the phases of the terms e to the power j theta minus alpha k. Referring to the figure, this implies with phi1 the angle of the vector v1 and phi2 the angle of the vector v2, the contribution of the zero at z is beta k and the pole at z is alpha k to the value of the phase of the frequency response at frequency theta 0 is equal to phi1 minus phi2. The pole zero plot of a second order system HZ with two complex conjugated poles at z is alpha and z is alpha star and two zeros at z is 0 is depicted in the figure. In this example, we vary the absolute value of the parameter alpha, which is an indication of the distance of the poles to the unit circle. The angle is kept constant and equal to pi over 4 radians. Complex conjugated poles imply that the coefficients of the frequency response h e to the power j theta are real. The magnitude and phase response plots show the result when the absolute value of alpha is equal to approximately 0.7. When increasing the absolute value of the parameter alpha, that is, decreasing the distance of the poles to the unit circle, the peaks in the magnitude response plot at frequencies plus or minus pi over 4 becomes higher and sharper, and the phase change at these frequencies increases. This ends this video in which we showed how to use the Z-transform to analyze a system. Thank you for your attention.